Okay, hey guys. So last week we started talking about further mechanics. The first thing we did was we looked at two things. We looked at impulse and momentum. These are two big areas in further mechanics at A level, and really we can use them in loads of different mechanical situations. So I thought I'd just do a recap of those two. So first things first, we defined impulse I, which we said was a change in momentum. So mathematically then, we said that I was equal to delta P. And if you remember from last week, we actually also defined momentum in thermal, where we said momentum was equal to the mass times by the velocity of some particle. So some particle in motion will have some mass m and some velocity v. So actually when we talk about impulse, we're changing about some kind of collision or interaction with this particle such that either its mass or velocity changes. Often it will just be its velocity, and that's what causes impulse. But actually, this is quite a basic definition here of impulse. We have a much better one, and we get that by considering my boy Newton's second law. So that's Newton's second law. And if we consider this, if you remember, the second law states that the force acting on an object is equal to its mass multiplied by its acceleration. So when we apply a force, we get an acceleration, and the sort of exchange rate there is its mass. But we can explore this a bit further. If we say that acceleration actually is just a change in velocity per unit time, for a constant mass, and that's important that I say that, for a constant mass, what we can do is we can take this m up inside the delta, so the mass doesn't change. That's mv over delta t, and that gives us mv, of course, is just our momentum, so we get that force is equal to the change in momentum per unit time, so rate of change of momentum. So just rearranging that slightly, we can get that the change in momentum, which we've said is impulse, is going to be equal to a force multiplied by a change in time, and that's really big. That's a much better way to describe this. So what's this saying? Well, it's saying a couple of things. If we have some change in momentum in a situation, so a collision, say something coming to rest after being in motion, it's telling us that there is going to be some force applied which is dependent on the time which this collision actually happens over. And what we actually explored a little bit last week was we looked at sort of graphs for collisions. So I'll just draw a couple here just to make an example of this. We looked at collisions where we had a force. We were measuring the force of these collisions against time, and what we saw was that if I just draw a really basic collision, something like this, so you've got some force acting over some time, we saw that this area under the curve here is actually equal to the change in momentum, and therefore is equal to our impulse. And what we found was, for any collision where the impulse is the same, so say a car hitting a wall, which you might be familiar with, so a car hitting a wall starting off at some speed v, and then coming to rest, so this would be mv, our momentum, and then at some point later coming to rest with the walls having no momentum, then we can plot that, and the area under the curve is our impulse. And what we saw was we can actually change one or the other of these parameters based on this equation, this, as we'll discover in a second, the impulse has to remain constant all the time. And what we said was, well, why don't we reduce the time that this collision's happened over? Okay, we know that the impulse has to remain constant, so what happens is your force becomes quite extreme. So in this case, this might be an example like hammering a nail into a block of wood at a party or something like that, and you want to apply as great a force as possible. So you're going to reduce this force down to as small a time as possible. Sorry, you're going to reduce the time as small as possible, and that will give you a maximised force. So this peak up here will be your maximum force. So an example with nailing a nail with a hammer, you actually want to pull back the hammer as quickly as possible so that you reduce this time and therefore end up with a really increased maximum force, remembering that our impulse here, the area under the curve, must stay constant. Something else we looked at was if we have the opposite case and we want to really make the time over which this collision happens as extreme as possible. So an example for that would be crumple zones in a car. So here we would be maximising the time so that we can have a smaller force. So our force in this case would be much smaller. Whoops. And in that way, so in the example of a car, therefore this would be things like crumple zones, like airbags, seatbelts. They make the collision happen over a much larger time so that the force is reduced and nobody gets hurt. So this is, if you like, just some everyday examples of where impulse is used. And something else actually from this is that we looked briefly at, or we can look briefly, sorry, at sort of an average force. Obviously in each of these graphs we have some maximum force in each case, but we might be at times interested in talking about, well, on average, what is the force applied over the whole of this collision? So I'll call that F bar, and that will just be equal to the impulse over the time that collision happens, or if you like, it will be the rate of change of momentum. So it will just give us an average force as opposed to plotting a graph and finding the maximum force in these places. So that's impulse, just a brief sort of recap of impulse. So I'll just rewrite that up here. Now, one nice thing with impulse is that we can actually prove the law of conservation of momentum. So what I'll do next is just actually derive that. So the conservation of momentum law simply says that if I've got some collision situation, so I'll just take two arbitrary masses, I'll call them mass A and mass B, a smaller mass. The conservation of momentum just says that should these two collide, the total momentum before must be equal to the total momentum after, and that has to be true based on this derivation that I'm going to show you now. So what we can do is we can consider these two particles. So A is moving left to right, B is moving right to left. They're going to collide, and what we can do is we can sort of take this collision and say, well, what happens at the moment, exactly at the moment they collide? So there will be a moment here where these two masses are in contact, and at that point we can say that, well, through Newton's third law, A will be experiencing a force because of B. I'll call this minus F because it's back in the right to left direction, and actually because of Newton's third law, likewise B will be experiencing a force due to A, so that'll be F. And what we can say is, from this situation here to the situation after, actually there's going to be, or we can say that there will be some impulse, so I can consider the impulse on the system, and that will be equal to the change in momentum for A plus the change in momentum for B. Okay, so let's do this. One last consideration we need to make is that we need to say that this whole collision lasts some time, delta t. So just substituting in then, the change in momentum for A is going to be minus F delta t, and for B it's going to be plus F delta t. Whoops. Since they both have experienced this equal and opposite force. When you do this, we see that the impulse is 0, and that means there is no change in momentum, which really, quite simply just proves our conservation of momentum law. The one thing that we actually get from this as well, or one thing that we should say, is that this is true only for closed systems. So there's no external source of force or energy sort of getting in our, or interfering with our masses. This is only for closed systems. Okay, so that basically is a run through, and then from that derivation, more explicitly, what we can say is for any collision, so we might have some before and after situation. Again, I'll take two masses, A and B, different size masses. So before, they might have some velocity each, they will collide, and then after we'll have some situation where, we're just taking general directions here, they might be moving away from each other again, and all we say is the total momentum, so the sum of the momentums before, is equal to the sum of the momenta after. So more generally, before, our momentum is going to be the mass times the velocity of body A plus the mass times the velocity of body B, so that's mu AU, I'm just denoting the U for before, and that's going to be equal to the mass and the velocity after of A plus the mass and the velocity after of our body B. So that then is our final conservation of momentum equation, and that's what we'll use every single time. Okay, so this is the first of a couple of videos this week. The next video I'm going to put together a quick recap of some circular motion. So see you later.